Rick, what's 1A asking me to find? Or did you say orbit? So if I see the word orbit, my first thought is gravity is what's pulling me in a circle, and since they said speed, I'll use the circular equation that has speed in it. One of the m's cancels, one of the r cancels, and I get v equals the square root of big G, big M over r. And I quickly crunch the numbers. Do you get 702? Yes? So I would give you 1 mark for the first equation, half mark for getting v by itself, and a half mark for the answer. But as always, if you got the right answer, 2 out of 2. What's the kinetic energy? I just went to half mv squared. I happen to have the v still on my calculator, and I got a kinetic energy of 6.16 times 10 to the 8th. I can't remember if it was in this class. Might have been in this class. Somebody got that 702 when they were doing this, and they came to me and, Mr. Dewitt, that seems really small. Brisa, what's the radius of the Earth? 6.38 times 10 to the what? What's the exponent on this radius? 10 to the? That's 2 powers of 10. We're 100 radiuses away from the planet. We're far enough away that gravity isn't that strong. We don't have to be going very fast to stay in our orbit, so you have a small speed and a small kinetic energy, because you might recall most of our kinetic energies were like 10 to the 9th or 10 to the 10th or even 10 to the 11th. So why don't we just put all of our satellites out there? If you calculated the change in potential energy, even though you saved some fuel on the kinetic energy, I'll bet you the change in potential is probably going to be in the 10 to the 11th, 10 to the 12th range. You don't come out ahead. It costs way more rocket fuel to just get up there. Hey, Brees, what's number 2 want me to find? Did you say orbit? Gravity is what's pulling me in... Oh, I guess since they gave me the period, I'll use the circular motion equation 4 pi squared r over the period squared. Again, one of the m's cancels. Does an r cancel this time? In fact, usually what I do for this equation, Bryce, is I cross out the r squared in my head, I multiply it there, and I just put a cubed there, and that's usually, Devin, enough for me now to do my cross multiply, get whatever it is by itself, because then I think I can say to myself, I'll have a big G, a big M, and a t squared, yes? And on the bottom, I'll have a 4 and a pi squared, yes? And then I'll have an r cubed. Oh, Brees, how do I get rid of a cubed? Oh, boy, I get to use a new button on my calculator. Cool. Big G, I know. M is mass of the Earth. I got out my calculator. And do you get 1.80 times 10 to the 7th meters? If you got that, 2 out of 2. Otherwise, I notice I wrote 1, 2, 3. You know what? Probably same as 1 mark for that, half mark for that, and a half mark for the answer. Most common mistake on this one, kids cancel out an R, or they square root just because they're not thinking and they're so used to doing a square root. They might even write cube root and they hit the square root button on their calculator. I've seen that happen a gazillion times. So don't do that. You want a little hint about your test? Yeah? Did we have to use a brand new calculator button on that question there? Does Mr. Dewick like it when you have to use mathematical functions that you've learned in math that we get to apply in physics? So Mr. Dewick has said he'll ask you orbital questions, and he has said something like, well, I can give you any one of orbital speed, orbital radius, orbital period, or orbital altitude. There's at least a couple of them, I guarantee I'm going to do the cube root one, because, oh boy, it's so cool. Cube root. What's B asking me to find, Taylor?
Potential energy.
Relative to what?
0 at infinity.
Now, why did I say that? That's my way of reminding you, make sure you use the cosmic one. I probably won't use that phrase on the test. I'll expect you to clue in. We're in outer space. G is changing. I can't use MGH. And so I used potential energy equals negative big G, big M, little m over R, and I got negative 2.66 times 10 to the 10th joules. Mr. Dewick, we're above the Earth. Why do I have negative potential energy? Where did we define 0? All the way out at? So here, the negative actually makes sense, because to get to infinity, you would have to add energy. You would have to burn fuel. So you would, in fact, I can tell you exactly how much energy you would need to add. 2.66 times 10 to the 10th joules of fuel would need to be burned to get you to infinity. So the negative works okay. Speaking of works, Devin, what's number 3 asking me to find?
Work.
To stay in orbit or just to lift the satellite up?
Just to lift the satellite.
So we're not in orbit, so we're not going to have any kinetic energy. So I started out by saying work equals the change in potential plus the change in kinetic, but I was able to cross out the change in kinetic. Now, if it had said how much work to put in orbit, and there will be one question on your test where I do that, don't cross out the change in kinetic. This is something I've tried to help you realize. You're not floating in outer space at rest and in orbit at the same time. That's impossible. You have to be moving while you're in orbit. Here, though, just to save time, I only asked for that. Devin, what's changing anything?
Minus initial.
And this is where we decided to use that Ditto mark approach. This is where I wrote out the first one carefully, and then I said, oh, you know what? The second one, that number is the same as that. That number is the same as that. That number is the same as that. All that's changing is here. And I noticed that that 4.5 times 10 to the 5th was an altitude. Don't give me any altitude. I had to then add the radius to it of the Earth. So that's why it's 4.6 times 10 to the 5th plus 6.38 times 10 to the 6th. And then what was the trick that I showed you that we're going to do for these questions? You do one fraction at a time, Alec, and then you just backspace and edit and do the next fraction. It's less typing, and more importantly, it's less error. How many times have you folks asked me, Mr. Duke, why did I get the wrong answer? It's been a calculator typo. There's just so much room to do calculator typos. We want to get rid of those. So I typed that first fraction, and I got negative 3.7612 times 10 to the 11th. I went backspace, delete, did this second fraction. I got 4.0324 times 10 to the 11th, and ended up with positive 2.71 times 10 to the 10th? Or the 11th? Is it to the 10th? Okay. Oh, yeah, it's 10th. Yep. That would give you 4 marks. If you didn't get the right answer, then I would give you a half mark if I saw that, a half mark if I saw that, a half mark for that, a half mark for that, a half mark for that number, a half mark for that number, and then 1 mark for the answer. That's a terribly messy answer key. I was doing that in a rush. I'll do a better answer key on Monday with my other block when I have the slightly longer class. Can you give yourself, on your take-home quiz, a lovely score out of 17, please? And then pass them inwards. The person in the middle, put them in a nice, neat pile. So if I've done my job right, you're not going to learn anything new today, Devin. But cool stuff. No new topics. By the way, this unit, 3 equations. Fg equals big G, big M, little m over r squared. Potential energy, cosmic potential energy relative to 0 and infinity, negative big G, big M, little m over r. And then I defined little g, gravitational field strength. That's the third equation. Let's look at asteroid impacts. It says this. Suppose a 45,000 kilogram asteroid is traveling at 5.67 times 10 to the 4th at a distance of 1.2 times 10 to the 7th meters from the center of the Earth. How much kinetic energy would it have if it impacted the Earth? Okay. Pierce, is this question asking me how much work? No. And the reason I keep doing that is I noticed on the energy test, some of you were trying to do everything with work. No. It'll be, if it says how much work, use work. If it doesn't, probably don't. Are we in a stable orbit here? How do you know? Because we're crashing into the Earth. If you can do one or the other. You can be in a stable orbit, then you're not crashing into the Earth, or you're not. So are we in a stable orbit here? So I can't go, gravity is what's pulling me in a circle. Is there a change in height? Is there a change in speed? Is there a yucky curvy force? You know, this is a job 4. How am I going to approach this? Oh, we were doing so good. Yeah, no kidding. That's why you didn't say anything. See, if you knew the answer and you didn't say anything, that's even dumber than blanking out, right? So help them out, folks. What? Conservation of energy. Now, Pierce, you did blank out. What was another way? Just the fact that it says how much KE might have been a hint to try conservation of energy as well? Yes? KE final plus PE final. Now, we traditionally, whenever we wrote out this equation, we would ask, are any of these zero? Are we ever at rest? No. Now, if I wanted to make this question a bit easier on your test, I might have the asteroid start at rest instead of starting at 5.67 times 10 to the 4th. But, okay. Is potential energy ever zero here? Where would it be zero if we were all the way out at? We're not here, so none of those are going to be zero. What are we trying to find? Which one? Initial or final? Final. You know, before I do anything else, I think I'm just going to get KE final by itself. I think I'm going to minus this to that side. And I'm going to get KE initial plus PE initial, take away PE final. And Pierce, do you mind? I'm going to write the KE final on the left by itself because that's where we always have the thing that's by itself. Now I'm going to write this out. Pierce, what's kinetic energy been since day one? Yep. Oh, wow. Lost everything there. A half mv squared. And then there's a plus. Can I use mgh? No, we're cosmic. So it's going to be plus negative big G, big M, little m over R initial. And then minus negative big G, big M, little m over R final. I think I know all the values. I think now we're at the plug and chug stage here. This is going to be a fair bit of plugging and chugging, but that's okay. So kinetic energy final equals a half 45,000. Brisa, what was the power of 10 on the mass of the Earth? I'm sorry, that was the radius. What was the power of 10 on the mass of the Earth? 24. This has a power of 10 of 4. This is not very big. This is, because 10 to the 20th times smaller, 10 to the 20th trillion, quadrillion? So a 45,000 kilogram asteroid, that may seem big to us. Meh. Now, we are ignoring air resistance. In real life, this thing, a lot of it would burn up in the atmosphere, thank goodness. But that's beyond our ability to calculate right now. What was the initial speed, Pierce? I've scrolled down. 5 squared. Take away 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 45,000 divided by, what's our initial? Not the Earth, because we're not starting out on the Earth this time, Alec. We're ending up on the Earth. Our initial is going to be where we started in space. The number that I gave you, is that a radius or is that an altitude? Do I need to add the radius of the Earth to that one or not? Oh, it says from the center of the Earth. So 1.2 times 10 to the 7th. You know it's a meaty, tough question when I've run out of room and I still need to write one whole term. Then there's going to be, Pierce, what's a minus minus the same as? So I'm going to start right here. Plus ditto mark times ditto mark times ditto mark divided by, and our final radius is the radius of the Earth. Deanna, have you seen those before? I'm saying that number is going to be the same, that number ends up right there, and that number ends up right there. So we're using that to avoid having to rewrite a bunch of stuff. And yeah, folks, it's going to be calculator time. Am I going to do this all in one step? No, one term at a time here. So the first one isn't too bad. A half m v 5.67 times 10 to the 4th squared. Our kinetic energy is positive 7 point, you know what? I'll go to 5 sig figs, 7.2335. Times 10 to the 13th. And then I have takeaway. Am I wrong?
Why didn't it work?
Why is what?
Because
I didn't hear your question.
It says like double, like work.
Oh, why did I write work? I don't know. Stupidly. Because I was doing a change in potential plus a change in kinetic. Can be for both of you. Remind me later. Or whichever one of you spotted it first, or was it simultaneous? We'll make it a team effort. Kiana, either put the minus there, or you can make this negative on your calculator, but just don't do both. I've got the minus there, so I'm going to type it as a positive into my calculator. 6.67 times 10 to the negative 11. Whoop. Go. Come on. To the negative 11 times 5.98 times 10 to the 24th times 45,000 divided by 1.2 times 10 to the 7th. Do you get 1.4957 times 10 to the 12th? No, yes? 1.4957 times 10 to the 12th. And then there's going to be a plus sign. And what we decided was, what? It's way easier to backspace than retype this. So I'm going to backspace. All the top numbers are the same. I just need to change the bottom number to 6.38 times 10 to the 6th. And I get 2.8133 times 10 to the 12th. And now, add them up. What do you get? How much energy will this thing have as it hits the Earth? Rick, what'd you get? Sorry, you're going to try it again without people talking? Sorry, what was that? 7.? Hang on, we're going to try it again. Guys, I'm sorry, I'm trying to hear his answer. 7 point?
7.36 times 10 to the 13.
Is that right? 7.36 times 10 to the 13th joules. Is that a lot? Is that a lot? Justin, turn the page over and read me the first sentence.
The atom bomb that exploded over Hiroshima had around 6.3 times 10 to the 13 joules in energy.
This is slightly more than the first atom bomb. Is that a lot? It's a fair bit. This would do some damage. And this isn't that big an asteroid. Okay? I'm not trying to scare you. I am trying to say to you, as you get older, push for some money to go into space research, because we are a fragile little blue planet, and we have had plenty of asteroid impacts in the past. I think it was in 1910, over Siberia, we believe a meteorite must have exploded, and it must have been a big one, because for hundreds of miles around, all the trees got knocked down like matchsticks from a central location. So we think one must have exploded in the air. There were hunters in the area that recorded seeing something bright and a loud noise. Probably some people died, but back then in Siberia, we didn't know who lived where, and probably some animals as well. And we had the meteorite that hit Russia a couple of years ago, you saw in the news, right? Oh, if you do ever see a meteorite in the sky, a bright light in the sky, stay away from glass windows, because there's going to be a sonic boom. Most of the injuries from the Russia meteorite were people who saw the bright light, rushed to their window, looked out the window, and then a few seconds later the sonic boom shattered the window and they got glass splinters in their eyes, probably not, or in their face. Not safe. Hey, how fast is this going? Well, we have kinetic energy equals a half mv squared. Trevor, how would I get the v by itself? What will I do with the m? And then you could divide by a half, or I like to times by 2 because it looks prettier. That would give us v squared equals 2 ke divided by m. Trevor, how to get rid of a squared? Yep. And hopefully you still have the kinetic energy on your calculator. So times by 2, divide by 45,000, square root. How fast is this puppy traveling? What do you get?
5.7 times 10 to the 4.
Give me 3 sig figs, please. 5 point what?
5.72 times 10 to the 4.
That's about 57 kilometers per second. If you divide that by 1,000, that's pretty fast. This would almost certainly be burning up in the atmosphere, and so some of the energy, in fact, hopefully most of the energy, that whatever we got 10 to the 13th, would not end up impacting into the ground. Hopefully much of it would transfer into light and heat, which at least is a little easier on our planet and on us. But there you go. And I already showed you the Neil deGrasse asteroid video. Second little mini topic, geosynchronous satellites. Geosynchronous satellites are cool. They maintain their orbit over the same place at the Earth at all times. Almost always they're circled around the equator. So if I am the Earth and this is a satellite, and I want the satellite to stay above the same place the entire time, what must the period of the satellite be? 0? No. The same, what's the period of the Earth? You all know this, don't look it up. It's in your head. In hours, please. 24 hours. Okay? But we don't do physics in hours. Convert that to seconds. Times by 60, times by 60, what do you get? You get 86,400? In fact, I think on your formula sheet, that's what it says the period of the Earth is as well, right? It says 86,400, right? It says 86,400, right?
Yeah.
It says 8.64 times 10 to the 4th, right?
This is 8.61 times 10 to the 4th.
What? It says 8.61? It says 86,100? That's 300 seconds we're missing. That's 5 minutes. Have you been lied to? Is the period of the Earth not 24 hours? Now I'm a little scared here. What's going on? It's not a typo. Pause the video for a second. What's the orbital radius of such a satellite? Are we in orbit? Gravity is what's pulling me in a circle. Which version of circular acceleration am I going to use? Oh, I know the period. It's a capital T. Yes? Does an M cancel? Yep. Ooh, does an R cancel? No, in fact, Devin, what I told you I typically do is I cross out that R squared and make it a cubed over there, because that's an easier equation to deal with. And now stuff moves diagonally. I multiply or I divide. I get R equals big G, big M, T squared over 4 pi squared. That's R cubed. How to get rid of a cubed? Cube root. So geosynchronous satellites are really, really handy because, for example, if you have a satellite dish, then it can stay pointed at the same area the whole time. It doesn't have to go searching for a satellite. Many of our GPS satellites are geosynchronous. They're really useful. But they have to be at the same radius. It's not that crowded up there right now. Probably in 1,000 years or so, it's going to start to get crowded up there. We'll have to come up with something. But I'm hoping in 1,000 years or so, we have Star Trek technology and have moved beyond just having low Earth orbit satellites. What do you get? It's going to be fairly big. I think it's in the 10 to the 7th or 10 to the 8th range. I think in the 10 to the 7th range. Might even be further. I can't remember. What'd you get, Taylor?
Working on
Oh.
the take-home quiz search.
No, you're staying on the lesson here and not working on the take-home quiz. Do you think maybe some of this might be showing up on tests in the future?
Isn't this stuff showing up on tests as well?
Yeah, but I think you're making a priority mistake. What'd you get, Connor?
42 million,
Can you give it to me in scientific notation, please?
4.2.
4 point what? 3 sig figs.
4.23.
4.23 times 10 to the...
7.
Is that right, folks? Yeah, 4.23 times 10 to the 7th. Okay. The last little bit I don't have written up for you, but it's going to be on your test. So you need to get on a blank piece of paper, please. You need to get on a blank piece of paper, and as a heading, you can write, black holes are cool. No, Mr. Dewick. I screwed up the title. How black holes are cool. Are you kidding me, Mr. Dewick? Let's try that again. Black holes are very attractive. Oh, that's better. Black holes are very attractive. Much better title than black holes are cool. I did tell you, and if I haven't, I'll repeat myself. I'll make sure you know now. I am going to do at least one question on your test where we go near a black hole. I want you to get used to the fact that you get some pretty big numbers. And then we also want to talk a little bit about, we can now handle black hole physics. So what I'd like you to do as a title, you can write black holes are very attractive. And then just write down 1A. You can decide how much of that you want to write down, whether you want to abbreviate, whether you want to just write down the data. But don't write B yet because we might need more space than I've given you. I'm not sure. So black hole has a mass of 7.2 times 10 to the 31 kilograms. There are what are called supermassive black holes. We're not looking at those. But a standard black hole, Alec, usually has a mass of between 5 to 50 times the mass of the sun. The sun is just a little bit too small to form a black hole. It will form a red giant in its death. So we have a black hole that has a mass of 7.2 times 10 to the 31 kilograms. The sun is 10 to the 30th, so it's a little bit bigger than the sun. Suppose a spaceship is 9.6 times 10 to the 9th meters from the center of the black hole. Alec, what's this question asking us to find?
Gravitational field strength.
Did they say gravitational force or gravitational field strength?
Field.
So is that going to be, don't write this down, that? Well, no, I would have said force. What symbol have we been using for gravitational field strength, folks? Little g. It wants us to find that. And probably on your blue sheet, you wrote the universal little g gravitational field strength equation. You probably, because I told you to, wrote, well, that's equal to big G, big M over R squared. But Devin, I did not put that on your yellow sheet because I'm mean. No, I did put it on your yellow sheet. No, you didn't. Yes, I did. Devin, you have your blue sheet there? Because the blue and the yellow sheet are roughly identical. Look at the gravity section. What's the first equation that I gave you?
Fg equals G M1 M2 divided by R squared.
The second one is potential energy. Skip that. What's the third equation? I defined little g. What did I say little g was?
Fg over
The force of gravity divided by...
mass.
Everybody look up. 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 Connor, you too. Look up. Everybody looking up. Rick, you too. I'm not going to stop until I see everyone's eyes. Here is how I defined little g. If you take... Look up, Connor. Just don't write. Just watch. If you take the force of gravity... Here is how I define little g. If you take the force of gravity and you divide out a...
Mass.
if you take the force of gravity and you divide out a mass, it is on your sheet. I think that's a fair derivation for me to expect you to do. The fraction vanished. Oh, and then M just realized this mass is big M. Okay. It's on there. I think that's a reasonable derivation for me to expect of you. Okay? So, you know I just like giving you equations that we can figure out. Hey, what is the gravitational field strength at this location? I'm going to give you a hint. It's going to be bigger than 9.8. 6.67 times 10 to the negative 11. 7.2 times 10 to the 31 divided by 9.6 times 10 to the 9th squared. What'd you get, Josh? 52, almost even, yeah? 52.1 or something like that? But almost exactly 5 times bigger than Earth's, because Earth's is really close to 10. Units for gravitational field strength? You can say newtons per kilogram. What else can you say? Since it's also the acceleration due to it's also meters per second squared, because it's force divided by mass. That's also A. Okay, so I'd take either of those. Just, on your calculator, change the 10 to the 9th in the bottom to a 10 to the 8th. What if we went 10 times closer? Now what's the gravitational field strength? It's getting bigger. What if we go another 10 times closer? It's getting bigger. It's going up by 100 times every time. And this is why black holes, when you're near them, act so strangely, because just a small change in radius can lead to a massive change in the gravitational field. In fact, there would come a point where the difference between the gravitational field on your feet and on your head was enough that your body would split in half. Okay? And then those chunks would split in half. And then those chunks would split in half. The fancy word for split in half is bifurcate. We have a name for that. Does anybody know what we call it when you fall into a black hole? This process of splitting in half and splitting in half and splitting in half and splitting in half and splitting in half? It has a great name, because in physics we know how to name things, unlike biology. It's called spaghettification. It's true. It's called spaghettification. Hey, what's the escape velocity required? I am going to ask you an escape velocity question on your test. I have not given you the escape velocity equation on purpose. How can I figure out escape velocity? Pierce, coming back to you. Did this question say how much work? So I'm not going to start out with work. Are we in orbit? Not if we're trying to leave the planet or the star or the black hole. We're not. There is going to be a change in height and a change in speed and a curvy force. We solve for escape velocity. This is why I said it should be called escape speed with scalar conservation of energy. Are any of these zero? We said we're defining escape velocity as getting away, infinitely away from the black hole, out to infinity. And so, Taylor, we can say that's zero. And we said if we're going to do this perfectly with no wasted fuel, you're going to be slowing down, slowing down, slowing down, slowing down. We want you to coast to a stop exactly when you get to the edge of the universe. So we actually end up with the right-hand side being 0. The left-hand side is going to be a half mv squared plus negative big G, big M, little m over r. Since all of the finals canceled, I stopped putting initials because they're all that's left. So I stopped with little i's. We want to solve for v. Before I even solve for v, what would I do first to make this equation prettier? Even before that, you can cancel the mass on this line if you want to, Kiana, but I tend to just do that because then I get a lovely, hey, we're used to seeing equations where one thing equals something else, and then you're more comfy as to whether or not the mass does cancel. You're right, I could have done it on the previous line. How would I get the v by itself? Times by 2 and then? Screwed. This is escape velocity. Not on your formula sheet because, Henry, you can derive it. Escape velocity is the square root of 2 big G big M over R. What's escape velocity from this location? You know what? I got most of this on my calculator already. I think I can just backspace, stick a 2 in front of the 2.67. Learn to use your insert key. You do have an insert button. And I need to change the 9.6 times 10 to the 7th back to a 9th. Delete the squared. Square root of that. And by a wonderful fluke, just I was making up numbers, you get almost exactly 1,000,000 meters per second. Fluke. But okay, 1.0 times 10 to the 6th meters per second. I'm trying to read my audience here. Kiana, you're pretty nerdy. You might know this. Kiana, I use the phrase event horizon in part C. Do you know what the event horizon of a black hole is? Does anybody know what the event horizon of a black hole is? So the event horizon is that spot where once you go closer than that, escape velocity is bigger than the speed of light. It's where no more light starts escaping the black hole. Further than that, you still have a theoretical chance of getting away. Light can get away. Closer than that, you're out of luck. So C says, at what radius from the center of the black hole does the event horizon begin? To solve it, we're actually going to start with our escape velocity equation. Write that down. All we're going to do is we're going to let v be the speed of light and solve for r. That's going to be where the event horizon begins. So I'm going to get a slightly different equation. I'm going to get C equals 2 big G big M over R. Remember that from last year? The speed of light is symbolized by a letter C because it's the constant. Where is the R right now? Inside what? Square root. You learn this in math. Square both sides. Square that side and square that side. We end up with this. C squared equals 2 big G big M over R. How would I get the R by itself? Where is the R right now? On the... So times it to the top and move the C squared down. Yeah? I think you'll get this. R equals 2 big G big M over C squared. Hey, crunch that. What is the event horizon of this black hole? Oh, what is C? It is on your formula sheet if you've forgotten. I think it's 3 times 10 to the 8th, yes? But it's on there. Speed of light in a vacuum is on there somewhere. What do you get? What'd you get, Connor?
Not the answer.
What'd you get?
0.008.
Yeah, I don't think that is the answer.
106,000 or...
100. This one actually I think works out evenly. Yeah? 106,000, like 720 or something like that? Yeah, like bang on.
Yeah.
No decimals, which is, again, total fluke, but I'll take that. 106,000. Is it 720? Not meters per second, it's a radius. Now, that's also the radius beyond which this star has to collapse. If the star is bigger than that, it can't form a black hole because the escape velocity speed is inside the star somewhere. Well, who cares? We have a fancy name for this. We call this the Schwarzschild Radius. This, suppose our sun began to collapse, keeping its mass but decreasing its radius. At what radius will it become a black hole? This is called the Schwarzschild Radius. The Schwarzschild Radius occurs at the same location as the event horizon. In other words, we're going to solve exactly the same equation. R equals 2 big G big M over C squared, but this time let M equal the mass of the sun, which is on your formula sheet. I think it's 1.98 times 10 to the 30th, but don't quote me on that. What do you get? How small would the sun have to be before its light would vanish because its light could not escape its own gravity? That's what by the way, that's what a black hole is. A black hole, they may still be giving off light inside there for all that we know. We don't, but it's just the light can't get out. So to us, they're black. What do you get? Connor B, what'd you get? You broke your calculator?
Yeah.
Wow, that is a sad story in one sentence.
I put it into the wrong mode.
Oh, you put it in the wrong mode?
Yeah.
Do you have a reset switch on the back?
No, I got it.
Oh, so that was the answer then.
Oh, I can use it, so I don't know the answer.
I don't understand what he just said. You got it. Did you get 2,900 and something or other?
Yeah.
Right?
Back in 934.
2,930? This is how we know the sun can't ever form a black hole. When you add up roughly the number of protons and nuclei and stuff that makes up the sun, you can't compress it into that small a density. If you're wondering, how do we know how big stars have to be for black holes to form? We can... Oh, by the way, going back to this equation right here, if you're looking at a black hole through a telescope, you don't actually see the black hole. What you see is a bunch of gas and dust spiraling around, and then everything vanishes. But you can measure the radius of where everything vanishes. And you can, if you know R, you can calculate the mass of the black hole. This is how we figure out the mass of black holes. Get you to the M by itself. Times by C squared, divide by 2G. It's a very trivial calculation. So a little black hole physics for you, some of which will be on your test. Okay?